Good morning, everyone. This is the relearning for the second standard on the most recent test, defining speed. Speed is how much distance an object moves in a certain amount of time. We also can call this how fast something moves. On the worksheet that I've provided for you, you should be able to find the spot where you should write down one of those definitions. While you do that, make sure you understand that the faster you drive, the higher the number is going to be. So if I drive 40 miles an hour, I'm moving at a faster speed than if I drive a shorter distance in that same amount of time. Also, we're going to be looking at a lot of graphs, so it's important to remember what the definitions of independent and dependent variables are. The independent variable, which will be time in all of the graphs we look at today, is an amount that's not affected by anything else being measured. A dependent variable is an amount that changes as the independent variable changes. And so in this case, that will be distance. So when you see distance time graphs, you're going to see the time is graphed on the x-axis because it is the independent variable, and the distance is graphed on the y-axis over here, which is the dependent variable. So let's look at some examples. You should have these first three filled out. So the first thing we need to go through is just the basics of, if you look at this kind of a line, what is the object doing? So on a distance time graph, if the line is flat, that means the object is at rest or not moving. Now, I've given a real life example, so you don't need to provide one for this line, but you should provide one for the next handful. Now, whenever the line is straight, that means it's moving at a constant or unchanging speed. Now, what's the difference between these two lines? Well, this line, when we looked at our graphs in class of what Tom was doing, the graph moving back would have been an example of like when Tom walked back from the party. Okay, so if it's going down, the distance from the start or home or the origin is decreasing. So a real life example would be walking home, assuming you're going at the same speed. So this would be, again, a constant speed because it's a straight line. But the distance from the start or home or the origin is increasing. I'd like you to come up with an example for this. So please take a minute. What would be an example for a real life example for that? Next, if we look here at my drawing of a graph, this was my best attempt to draw this. So in this stretch of time, it'd be a long time, and they didn't cover very much distance, versus this chunk of time here, short amount of time and a large amount of distance. And what this means is, if you see a line like this, the object is speeding up. So go ahead and please fill out, think of an example, a real life example for a time when something, a car, hint hint, is speeding up. Now if we do the same down here on this section, again we have time on the x and distance over here. A lot of distance has been covered in a short amount of time compared to this time. A little distance has been covered in a long amount of time, and that would be slowing down. So because it'd be going fast speed here and slow speed here, whereas here it's the opposite, slow and fast. So again, please come up with a real life example of a time when something that is speeding up. So we're going to look at a distance time graph. Mine says displacement. This should say distance. It's the same thing. You'll notice it's also measured in meters. So let's look at what's happening in the graph. Now, from time 0 to time 3, what's happening? Well, we see a line like this, and if we check what we wrote on the last side, we're going slow and then fast. That's speeding up. Between seconds 3 and 5, the object is at rest. Between seconds 5 and 7, it's moving at a constant speed, and the distance is decreasing. You could also write that. Same thing from 7 to 9, still going at a constant speed. And, and then same thing 9 to 12, it's a constant speed. Okay. Now, number 7 asks us to calculate how fast the cart was going. So we need to use our equation, speed equals distance divided by time, so between 5 and 7. So I'm going to find where on the graph we've got 5 and 7. Now, looks like at 5 seconds the distance is 120, and at 7 seconds the distance was 0. So that means that the cart went 120 meters, and we're only going from 5 to 7, so that's just 2 seconds. So you're dividing 120 meters by 2 seconds, and you get 60 meters per second. I think this is the number one area where people had a hard time, so make sure you understand where I'm getting those numbers from. Last but not least, we need to understand how the steepness of a line demonstrates how fast something was going. So number 8 asks which person, the one represented by the dotted line or the solid line, is going faster. And we're going to say it's the dotted line. So we're looking here. And how do you know? Well, the dotted line is steeper. And if we think about it like this, let's say this is 2 people running in a race. The distance they went is the same. So let's say this is Miss McConnell's brother Dan, and here's me. Here's my brother Dan, and there's me. Dan gets to the end of the race earlier. You can see the time is less than I do. And so he must have been moving faster. So we know that Dan is moving faster because the line is steeper. You could also write, we know that Dan is moving faster because he covers the same distance in less time, or something along that line. All right, so that brings us to part 2. You need to do this part on your own. Please turn this in to me, and if you have any issues, ask me for help. Thanks very much.